This chapter on systems contains information you need to know to effectively discuss the operation, characteristics, and use of mobile hydraulic systems in Caterpillar machines. Objective: you'll be able to identify and discuss the differences and similarities between open and closed center hydraulic systems. Hydraulic systems on Caterpillar machines are often referred to by the various types of components or features present in the system. For example, a pilot-operated system is one that incorporates pilot-operated valves. The most commonly used terms to classify mobile hydraulic systems includes open and closed center, fixed and variable displacement, manual and pilot-operated, pressure compensated, and load sensing. Hydraulic systems that incorporate electronic control devices are often called electronic over-hydraulic systems. This lesson explains the operation, characteristics, and use of these systems in Caterpillar machines. In this first lesson, we look at open and closed center systems. An open or closed center system refers to the type of directional control valve that operates the actuator. The hold or neutral position of an open-centered valve directs full pump flow to the tank. Ports A and B are blocked. When the valve shifts to this position, oil flows from the pump to port B, extending the actuator. When the valve is shifted to this position, oil flows from the pump to port A, retracting the actuator. When the cylinder is stalled out, the main relief valve opens, returning pump flow to the tank and protecting the system from excessive pressure. This ISO schematic represents the lift, tilt, and auxiliary circuits on a small Caterpillar wheel loader. Note that the direction control valves are open-centered, permitting pump flow to return to tank in the neutral center position. See if you can trace flow through the circuits in each of the valve positions. On this schematic, you should be able to identify the supply line from the pump, which is indicated by number 1, the lift circuit is shown by 2, flow to the lift cylinders is marked by the number 3, the number 4 shows the tilt circuit, and 5 indicates flow to the tilt cylinders. Number 6 identifies the auxiliary circuit, and 7 shows flow to the attachment cylinders. Finally, the number 8 indicates flow to the tank. On this simple closed-center system, the hold or neutral position blocks pump flow, which causes the main relief valve to open. When the valve shifts to this position, oil flows from the pump to port B, extending the actuator. When the valve is shifted to this position, oil flows from the pump to port A, retracting the actuator. When the cylinder is stalled in either extreme, the main relief valve functions the same as in the open-centered system, protecting the system from excessive pressure. This is part of the ISO system schematic for a Caterpillar backhoe loader. The 2 closed-center valves control the bucket and boom cylinders. See if you can identify all the various types of valves and trace flow through these 2 circuits. On this illustration, number 1 indicates pump supply, 2 identifies the signal to the pump, the bucket cylinder is shown by the number 3, and number 4 is the location of the boom cylinder. Objective: you'll be able to identify and discuss the differences between fixed and variable displacement hydraulic systems. A fixed or variable displacement system refers to the type of pump that supplies flow. The output of a fixed displacement pump is only affected by its operating speed. When the machine is running at high idle, the pump is always producing maximum flow. Consequently, these are very responsive systems. Many operators like fixed displacement systems because they can use the sound of the engine lugging to determine how hard they are working the hydraulics. There are some limitations to fixed displacement systems. Heat can build up because the pump is always running, passing flow through the system. and fixed displacement pumps require engine horsepower that could be used for other purposes when hydraulic power is not needed. Variable displacement systems use pumps that supply flow on demand. In this system, a pump control valve senses work port pressure and adjusts the output of the pump to supply only the amount of oil required. This type of hydraulic system is more fuel efficient. It also generates less heat, resulting in longer component life. This is a simplified schematic of a variable displacement hydraulic system. Note that the pump control valve is connected to both work ports by a double check valve or shuttle valve. When the directional control valve is in the center or hold position, pump flow to the work ports is blocked. The pump control valve senses the lower work port pressure and adjusts the pump so it only outputs sufficient flow to maintain minimum system pressure. This condition is called low pressure standby. When the directional control valve shifts, the higher pressure in the work port closes the double check valve, sending the higher pressure back to the pump control valve. This signals the pump control valve to upstroke the pump, sending more flow to the actuator. This orthographic cross-section represents a variable displacement pump and its control valve. Study it carefully. Pay close attention to the highlighted sections of the drawing. Number 1 indicates where signal pressure enters from work ports. Number 2 shows pump supply to the control valve. Number 3 is the large actuator. Number 4, the swash plate. Number 5, the small actuator and bias spring. And number 6 is the margin spool. When the implement directional control valve is in the hold position, flow to work ports is blocked and no signal pressure is being sent to the pump control valve. Since there is no signal pressure, pump supply pressure is enough to keep the margin spool up. This directs pump flow to the large actuator, which maintains the pump swash plate at a minimum angle. This state is called low pressure standby. In this condition, the pump is producing just enough flow to compensate for system leakage and maintain adequate system pressure to ensure good implement response. When the implement directional control valve is shifted, pressure from the selected work port is sent through the signal line to the pump control valve. This additional pressure works with the spring to push the margin spool down, allowing flow to the large actuator to drain to tank. The small actuator and bias piston can now move the pump swash plate to a higher angle, increasing pump output. This condition is called upstroking. As pump flow increases, system pressure also increases. As system flow requirements are satisfied, the margin spool moves to maintain a constant pressure differential between pump output pressure, or system pressure, and signal pressure. This pressure differential is called margin pressure and is equal to the value of the spring above the margin spool. In this condition, pump flow is relatively constant and being directed to the actuators. If the operator wants to slow the implement directional control valve is throttled back toward the hold position, reducing flow to the work ports. This change in flow requirements results in a higher pressure below the margin spool, moving the spool up and allowing more flow to be directed to the large actuator. The increased pressure to the large actuator is greater than the force of the small actuator and bias spring, so the swash plate moves to a reduced angle, reducing pump flow. This is called destroking. When the desired system pressure is achieved, the pump again returns to a constant flow condition. This pump control valve has another control stem that reacts to pump supply pressure and is set to open at a given maximum pressure. Called a pressure compensator or pressure cutoff spool, this valve works to destroke the pump to limit maximum system pressure. During normal operation, the spool is forced down by the pressure compensator spring. In a stall or maximum system pressure state, signal pressure is equal to pump supply pressure. The combination of signal pressure and margin spring forces the margin spool down. This would usually cause the pump to upstroke. However, since supply pressure was great enough, the pressure compensator spool is forced up. This permits supply oil to flow to the large actuator destroking pump and reducing flow. This feature eliminates the need for a main system relief valve in some systems. Maximum system pressure is set by the pressure compensator adjustment screw. In this illustration, the valve is in the rack-back position. Study the schematic carefully and trace flow through the circuit. This is a partial ISO schematic of the variable displacement system on a medium-sized Caterpillar track-type tractor. See if you can trace flow through the pump control valve as signal pressure changes. On this graphic, the number 1 identifies the end cover, 2 the dozer tilt, 3 the dozer lift, and 4 the steer. You'll be able to distinguish between manually operated and pilot-operated hydraulic systems found in Caterpillar machines. The directional control valves on Caterpillar machines are often manually or pilot-operated. On manually operated systems, control valves are moved directly by the operator's hand or foot, usually through some type of mechanical linkage. Many small Caterpillar machines are manually operated systems. Typically, manual operation allows more precise control of implements. Pilot-operated systems use small pilot valves to control the movement of the main directional control valve. They are used on valves that would be difficult for the operator to control, or on directional control valves that are remotely located on a machine. Larger machines often use pilot-operated systems. These systems reduce operator effort, resulting in less fatigue. This is an orthographic schematic of the hydraulic circuit on a large Caterpillar track-type tractor that controls ripper lift and tilt. The pilot spools are manually controlled by the operator. Both pilot and main directional control spools are shown here in the hold or neutral position. Note the location of each of the 4 control spools. Number 1 is the tip control pilot spool. Number 2, the lift control pilot spool. 3, the lift control spool. And 4, the tip control spool. To trace fluid flow in this position, pay close attention to the legend in the lower right corner. A, the gray crosshatch pattern, indicates pilot oil. The light gray dotted pattern, B, is the small pump section oil. The diagonal lines represented by C indicate pump section oil, and the solid black represented by D indicates return oil. When the pilot valve is moved to the shank out position, pilot oil is sent to one end of the main control valve spool and opens the other end of the main valve spool to tank. Pilot oil pressure can then move the main valve spool, which sends flow from the large implement pump to the ripper cylinders, retracting them. As you study the fluid flow, remember, on this illustration, number 1 points out the tip control pilot spool, number 2 shows the lift control pilot spool, number 3 the lift control spool, and number 4 the location of the tip control spool. The pattern legend in the corner shows that A is pilot oil, B is small pump section oil, C is large pump section oil, and D is return oil. Shifting the pilot valve to the shank in position reverses the flow of pilot oil, moving the main control valve spool and porting main pump flow to the cap end of the ripper tip cylinders. The numbers on this graphic again point out the locations of the 4 control spools, and the various patterns mean the same as in the 2 previous illustrations. This ISO schematic shows the pilot-controlled boom and bucket circuits on Caterpillar's larger hydraulic excavators. See if you can trace flow from the pilot valves to the main directional control valves. Take a moment to study the schematic. The number 1 indicates where flow travels out to the boom cylinders. Number 2 identifies that flow is headed to the bucket cylinders. Whenever you see the number 3, it indicates the location of a boom control circuit. The number 4 points out the bucket control circuits. Number 5 is the main pump, and 6 the pilot oil pump. Flow from the tank is marked by number 7. Objective. You'll be able to discuss the function of load-sensing hydraulic systems and their application in both fixed and variable displacement systems. Many Caterpillar machines are equipped with load-sensing hydraulic systems. That means the hydraulic system can determine how much load there is on the various implements and provide only the amount of system pressure and flow necessary to do the work. These systems generate less heat, have better component life, and in variable displacement applications, provide better fuel economy. Load sensing refers to any system that regulates flow to maintain a pump supply pressure at a fixed value above the highest work port pressure requirement. Load sensing can be achieved on both fixed and variable displacement systems. Load sensing in a fixed displacement system is accomplished through the use of a flow control or dump valve. This valve senses pump supply pressure and work port pressure and maintains a pressure differential between the two equal to the value of the spring. In a closed center system with the directional control valve in the hold position, the dump valve is open, returning pump flow to the tank at a lower pressure than the relief valve setting. When the directional valve is shifted, the load on the cylinder causes the dump valve to close and pump flow is directed to the cylinder. As the flow requirements of the cylinder are met, system pressure increases. The dump valve will open to meter excess flow to tank to maintain a set pressure differential between the cylinder pressure and system pressure. If flow requirements change, the dump valve will move to maintain the required flow rate to the cylinder and the differential between load and system pressure. This ISO schematic represents a typical fixed displacement load sensing hydraulic system. See if you can locate the flow control or dump valve and trace flow through the system as the load varies on the actuators. Load sensing in a variable displacement system is accomplished through the use of a variable displacement pump and pump control valve. The pump control valve senses pump supply pressure and work port pressure and regulates pump flow to maintain the desired pressure differential. The operation of this system is discussed in the lesson on fixed and variable displacement systems. This ISO schematic represents a variable displacement load sensing hydraulic system. See if you can trace flow through the system with the directional control valve in all 3 positions. Objective. You'll be able to identify and discuss the characteristics of pressure-compensated hydraulic systems. Many Caterpillar machines are equipped with pressure-compensated systems. This term is often used to describe certain pumps and valves and generally refers to conditions that limit output pressure. At Caterpillar, the term usually refers to control systems that produce a constant implement speed for a given lever displacement. Pressure compensation can be accomplished through the use of a pressure-reducing valve between the pump and the directional control valve. This valve senses downstream pressure at the control spool and higher work port pressure from the rod or head end of the cylinder. The pressure-reducing valve varies flow to the control valve in order to maintain a constant pressure differential across the control valve. This reduces lever efforts and gives the operator more precise control. In this example of a pressure-compensated system, the pump is producing more flow than the cylinder requires. Pump output pressure is 2,700 psi. Work port pressure is 1,000 psi, and the pressure created by the spring in the reducing valve is 50 psi. Under these conditions, the pressure-reducing valve limits pressure to the directional control valve to 1,050 psi, regardless of pump output pressure. The excess 1,650 psi is dissipated as heat. Since work port pressure is 1,000 psi, there's only a 50 psi pressure drop across the directional control valve. If work port pressure increases or decreases, the pressure-reducing valve will continue to maintain a constant pressure drop across the control spool. Since pressure drop is controlled, lighter centering springs can be used in the directional control valve, resulting in reduced lever effort and operator fatigue. It also eliminates the effects of varying engine speeds and changing work port loads on cylinder speed. 1. Pump output pressure. 2. Work port pressure. 3. Pressure created by the spring. This is an ISO schematic of a pressure-compensated fixed-displacement hydraulic system. Given a pump output pressure of 2,000 psi, work port pressure of 500 psi, and a spring pressure of 50 psi, see if you can calculate the pressure drop across both the pressure-reducing valve and directional control valve. Pump output pressure is again indicated by the number 1, work port pressure by the number 2, and spring pressure by number 3. This is an ISO schematic of a pressure-compensated variable displacement hydraulic system. The pressure-reducing valve functions the same as it does in a fixed displacement system, controlling pressure drop across the directional control valve. This system will generate less heat, since the pump control valve will de-stroke the pump when flow is not required. Objective: you'll be able to discuss typical applications of computer or electronically controlled hydraulic systems. Some Caterpillar machines are equipped with sophisticated computer or electronically controlled hydraulic systems. These types of integrated systems give the operator more precise control over the machine and are generally more productive and more efficient. This topic is an introduction to electronic hydraulic systems. We will examine two typical applications of this technology: an electronic power unit control and a work mode selector. The Electronic Power Unit Control, EPUC, is a microcomputer-based electronic device used to control hydraulic fluid flow. Its main function is to limit the hydraulic horsepower range of variable displacement pumps. The EPUC matches hydraulic horsepower to available engine horsepower, improving machine performance, noise levels, and fuel efficiency. The work mode selector permits the operator to configure a machine for particular operations. This excavator work mode selector, for example, has 3 settings: loading, sidewall crowding, and leveling. These settings determine which hydraulic circuits get priority. The benefit is increased implement control and higher production. Objective: you'll be able to apply your knowledge of Caterpillar hydraulic systems to your job by recognizing the characteristics of the hydraulic systems most commonly used on Cat backhoes, excavators, and wheel loaders. A wide variety of hydraulic systems are used on Caterpillar machines. Even machines in the same family may have significantly different features and characteristics. The reason for this is that each machine must perform certain kinds of work and compete in certain types of markets. Although each machine system is unique, the systems on these 3 machines are representative of those typically found on Caterpillar machines. The hydraulic system on the 910E is representative of those found on Caterpillar's smaller, utility-sized machines that have fairly simple hydraulic requirements. There are 5 primary circuits in the system: steering, brakes, bucket lift, bucket tilt, and an auxiliary attachment circuit. A 2-section fixed displacement gear pump provides flow for the entire system. The front section powers the implements, and the rear section supplies flow for steering and brake circuits. The system has a pressurized tank, fluid filter, and an oil cooler is optional. The implement control valves are open-centered and manually operated. The lift and tilt valve spools are equipped with electromagnetic detents in the raise and rackback positions. These detents work with electronic sensing devices on the lift arms and cylinders to provide automatic bucket positioning and lift kick-out. This feature eliminates the need to visually check bucket position and frees the operator's hands for maneuvering the machine. The 910E uses threaded gland lift and tilt cylinders, and all connections are fitted with O-ring face seals. This type of hydraulic system provides good, reliable service on machines that must compete in highly competitive, price-sensitive industries such as building construction. Some small utility-type machines, such as backhoe loaders, require fairly complex, sophisticated hydraulic systems. This 426, for example, has a variable displacement, load-sensing, pressure-compensated system that provides optimum performance for both the backhoe and loader functions. The hydraulic tank on the 426 is pressurized to prevent system contamination. The hydraulic filter assembly is located inside the tank. It consists of two filter elements, one for pump case drain oil and the other for return oil from the implement valve groups. All system flow requirements are met by a variable displacement axial piston pump. A pump control valve senses the highest pressure requirement from the loader, backhoe, and steering circuits and adjusts the pump to provide adequate flow. Implement control on the 426 is provided by closed-centered, manually operated selector valves. The backhoe and loader valves are pressure compensated to reduce lever effort and improve controllability. The backhoe control valve stack has 6 standard valves for stick, bucket, swing, boom, and stabilizer control. 2 optional valves can be added for extended stick and auxiliary control. The loader control valve stack has 4 standard valves, bucket lift and tilt, an auxiliary circuit for optional attachments, and steering. The tilt control valve spool is fitted with an electromagnetic detent and is mechanically connected to the tilt cylinder linkage. This system provides for automatic bucket leveling and the return to dig feature that improves loader productivity. Caterpillar XT3 hose, threaded gland cylinders, and O-ring face seals on all connections ensure a durable, dry hydraulic system. The swing cylinders are equipped with snubbers that cushion and slow the backhoe before it contacts the frame stops. Caterpillar backhoe loaders are versatile utility machines that excel at many digging and lifting jobs. The hydraulic system on these machines are designed for maximum efficiency. They can deliver full implement forces at any engine speed and feature low lever efforts, low heat generation, and low fuel consumption. The E-Series excavators, typical of Caterpillar's large, high-production machines, are equipped with sophisticated computer-controlled hydraulic systems. These systems provide fast, aggressive production cycles, responsive implement control, and efficient operation. This particular model features variable displacement, pressure-compensated, load-sensing pumps. Main implement control valves are open center and pilot-operated. There are 5 primary circuits: boom, bucket, stick, swing, travel, and a 6th auxiliary circuit for attachments. Main system flow requirements are supplied by 2 tandemly mounted variable displacement axial piston pumps. They are coupled directly to the engine flywheel. The pilot system is supplied by a single-stage gear pump which is driven by the rear piston pump. An accumulator in the pilot circuit provides smooth control of the implement circuits during multiple implement operation. It also allows limited gravity-assisted implement control when the engine is not running. Travel and swing motors are both fixed displacement axial piston type motors. The travel motor has an integral brake that is automatically set when pressure is no longer applied to the motor. This model is also equipped with a straight travel feature that keeps the excavator moving straight during simultaneous travel, implement, and swing operations. Hydraulic pump output is computer controlled and equipped with a power mode selector. The Electronic Power Unit Control, or EPUC, is a microcomputer that continually monitors hydraulic pressure, engine RPM, power mode selector and governor setting, and adjusts pump output to maintain a desired hydraulic horsepower or engine RPM. This improves fuel efficiency and ensures that nearly 100% of engine horsepower is available to the hydraulic system. The EPUC is also equipped with self-diagnosis capability. The power and work mode selectors permit the operator to tailor the hydraulic system to match the job requirements. These controls work by adjusting pump output and controlling the priority of various circuits. In this topic, you meet Jim Thomas, a field service mechanic with the local CAT dealership. According to his service manager, Jim is the best troubleshooter in the field. He is on his way out to a customer's job site. They called earlier today, said they were having trouble with one of their 980s. You are invited to go along with Jim and help him troubleshoot the machine. So hop aboard, buckle up, and good luck. You and Jim arrive at the job and are met by the customer. He's upset because the 980 they're having problems with was in the shop at the dealership only a month ago. One of the main implement pumps was replaced. The 980 seems to be acting the same way it did before the first failure, and the customer is convinced it's the same problem. He insists you save everybody's time and just replace the pump. Jim asks the customer when the problem started. He says you'll have to talk to the operator. After talking with the operator, you learn that they first noticed some problems with the loader about a week ago. The implement hydraulic system didn't have enough power. At first it wasn't too bad, but it's been getting a lot worse lately. In fact, the loader can now hardly lift a full load. The operator also believes the pump is faulty, since the lack of power is continuous. What do you think your next step should be? 1. Inspect the machine. 2. Replace the pump and save time. 3. Look at the service records. Or 4. Ask the operator to run the machine so that you can see the problem firsthand. If you answered 3, look at the service records, you're correct. You're still in the first troubleshooting step of making sure a problem really exists. The service records are a good source of information. On many field service calls, you might check service records before you leave the dealership. In this case, the customer has kept his own detailed service records. Checking the service records, you learn that the hydraulic pump was replaced about 6 weeks ago. It had over 6,000 hours on it, which is considered a reasonable pump life. Since the failed pump showed some signs of excessive wear, the tank and some of the valves were disassembled and cleaned to make sure no debris was left in the system. The new pump has only 230 hours of operation. However, the operator is experienced and the symptoms are obvious, so you're confident that a problem does in fact exist. The next step is to write down the problem as a simple statement. Which of these best states the problem? 1. The hydraulic system lacks power. 2. The machine is not working properly. 3. The pump is not producing adequate flow to fully power the implements. If you chose statement number 1, the hydraulic system lacks power, you're correct. It states the problem in the simplest terms. While it's true the machine is not working properly, statement number 2 is vague. You should be as specific as possible. However, you can be too specific, as in the case with the third choice. Statement number 3 suggests a solution to the problem by naming the pump as the cause. At this point, we're not sure what is causing the problem. Now that you've written down the problem in its simplest terms, what's your next troubleshooting step? 1. Inspect the machine. 2. Fix the problem. Or 3. Run tests and record data. Well, you will need to run tests, collect data, and fix the problem eventually. But you should first inspect the machine. A thorough visual walk-around of the machine reveals no leaks or obvious damage of any kind, and fluid levels are correct. Jim then asks the operator to start up the machine so you can see for yourself exactly how the hydraulic system performs. The problem is exactly as you have described it. The hydraulic system lacks power. So, the next step is to make a list of all possible causes of the problem. After checking the schematics in the service manual he brought along, Jim prepared this list of causes. Think about how each of these items could cause the problem you have observed. Then select each choice to see if your reasoning is the same as Jim's. Is the cause an incorrectly adjusted engine RPM? If the engine RPM is set too low, the pump would produce less flow, adversely affecting implement performance. What about a faulty control valve? A worn or broken control valve could be leaking internally, diverting some of the flow intended for implement circuits. Or a faulty or incorrectly adjusted relief valve. A relief valve could be opening at too low a pressure, diverting some of the flow back to the tank. The problem could stem from a faulty pump. If flow loss is too great, pump output will not be sufficient at higher pressures, adversely affecting implement performance. Several pump conditions could contribute to flow loss. Now that you and Jim have prepared a list of possible causes, it's time to perform some tests. Based on the information you have collected so far, you decide to check the RPM set point. You measure cycle times and drift. And you measure both system and pilot pressures. You could also check pump flow, but since that takes a little longer, you decide to postpone that test until after you eliminate some of the possible causes. With the engine running at high idle under normal conditions for operation, an engine set point indicator group was used to take RPM readings with and without a load on the engine. The difference between the two readings was 7 RPM. Acceptable tolerance is plus or minus 10 RPM. Incorrect implement cycle or travel times generally indicate inadequate flow. Here are the measured times compared with those specified in the service manual. On this machine, excessive implement drift can indicate faulty makeup valves, worn valve stems in the control valve sections, or worn piston seals in the cylinders. With hydraulic oil temperatures of 100 to 120 degrees Fahrenheit, 38 to 40 degrees centigrade, maximum permissible lift cylinder drift is 0.50 inches, 13 millimeters, in 5 minutes. Maximum permissible tilt cylinder drift is 0.75 inches, 19 millimeters, in 5 minutes. Measured drift was within these limits. Main system pressure was measured at 1,985 psi. Correct system pressure is 3,000 psi plus or minus 50 psi. Pilot system pressure was measured at 320 psi. Correct pressure is 335 psi plus or minus 15 psi. Now that you've finished testing and data collection, it's time to eliminate items from your list of possible causes and isolate the real problem. Which of these items do you think we can eliminate based on everything we know so far? 1. Incorrectly adjusted engine RPM. 2. Faulty control valve. 3. Faulty or incorrectly adjusted relief valve. 4. Faulty pump. If you eliminated incorrectly adjusted engine fuel pump and faulty control valve, you're correct. Engine RPM set point was measured and found to be within tolerance, so this item cannot be the cause of our problem. Since the lift and tilt circuit cycle times and drift were within specifications, it's unlikely that the control valve is a problem. By eliminating the first two items from your list, you have isolated two possible causes, the main relief valve and the pump. When you are left with more than one possible cause, start with the easiest and fastest to check or replace, in this case, the relief valve. When starting to readjust the main relief valve, Jim thought the plunger turned much too freely, so he replaced it, then finished adjusting system pressure. The hydraulic system responded immediately. The problem had apparently been fixed. The operator took the machine out and was satisfied with its performance. The repairs were apparently successful. But is the troubleshooting task completed? It is important to analyze the failure and try to determine why it occurred in the first place. Upon examination of the replaced plunger, you discover that the plastic thread lock was damaged. This probably happened when relief valve was disassembled, cleaned, and reassembled during the previous service. Vibration from machine operation probably caused the plunger to slowly back out over a period of weeks, reducing system pressure. The result was a gradual loss of hydraulic power. The job is finished when Jim fills out the service report, remembering to add his analysis of the failure.